electronic computer, often referred to as computers, are not brains. They do not think. They are not capable of planning, devising, or creating. But they can remember things in the sense that they can store large amounts of data. Data which can be made available at a rate of speed. For example, the electronic computer can solve an equation such as one by the French mathematician Pontecoulon for the motion of the moon. This same equation would take a mathematician 2 years to solve by manual method. You may not realize it, but the chances are that a machine such as this one, or similar to it, has already affected your everyday life and will most certainly affect your future. Electronic computers and data processing machines are being used extensively by science and industry for determining new markets and new products, making possible reduced inventories. The control unit serves as the nerve center of operations, instructing the other units. The input unit is used to feed initial data to the storage or memory unit. When the processing or arithmetic unit is called into operation and given certain data, it is capable of performing tens of thousands of mathematical calculations per second. When a solution to a problem is obtained, the information is transferred from the memory unit to the output unit. Answers to problems can be printed at a rate of 600 per minute. Electrostatic devices print answers at a rate of several thousand lines per minute. The chance of error in all these high-speed manipulations is extremely small. Computers can check their own results to ensure against errors. Because of their speed and accuracy, electronic computers are making it possible for man to explore fields of science in which answers to complex problems must be obtained in millionths of a second to be of value. But there was a time when problems did not demand so much speed, and a man could count and compute on the fingers of his hand. This was man's first digital computer, for the word digit means finger. As early as ancient Egypt, finger counting was supplemented by pebbles. Pebbles dropped into respective trenches in the sand represented ones, tens, hundreds, thousands, etc. The word calculus, from which we get the word calculate, means pebble. Calculation involved the slow process of removing excess pebbles from one trench and transferring pebbles to another. This crude computer was the forerunner of the abacus. Instead of pebbles, beads strung on wires represented digits or groups of digits and resulted in a more maneuverable instrument. This type of digital computer is still used with great skill in parts of the Orient. With the advent of the machine age, mechanical devices were taking the place of the hand in manipulating digits. This Parmelee calculator of 1850 was the first keyboard adding machine. The first practical rotary calculator using wheels to manipulate digits was this Baldwin, developed in 1872. The Brunsviga lever set calculator of 1891 operated faster than previous devices, making it possible to handle more calculation in less time. The need for faster calculating machines became apparent as the population expanded and more data had to be processed continually. The United States Census of 1890 was processed on this tabulating machine using punched cards in 1.5 years. Manual methods would have taken 8 years. Many other types of calculating machines were developed to handle the increasing volume of business, economic, and scientific problems. This early ENIAC electronic computer was used to solve problems in 2 hours that would have taken a mathematician working with a slide rule 100 years. Our electronic computers of today look extremely complex. This UNIVAC Lark fills an entire room. Like all computers, it is made up of 5 basic components, including input, control, storage, processing, and output. These 5 components are essential to all computers, regardless of their mode of operation. Complex as they look, electronic computers operate on a very simple principle. They receive only 2 signals. They make only 2 responses. Being electronic, they have circuits that can be opened or closed, switches that can be off or on. Its understanding and its answers are limited to these 2 possibilities. Since this is true, how can we translate reams of data, thousands of words, complicated formulas, into the yes-no signals that the computer can understand? The answer is binary arithmetic, a system that uses only 2 digits, 1 and 0. The binary number 101 equals 5 in the decimal system. Any number can be written in the binary system. 142,857 looks like this in binary arithmetic. This system of arithmetic is actually more simple than the decimal system, which uses the digit 0 and 1 through 9. In order to understand the meaning of a number, we must know the place value assigned to each digit in the number. When we write numbers in the decimal system, 1 in the first column or first place means 1, 1. 1 in the second place means 110 or 10. 1 in the third place means 100 or 100. 1 in the fourth place means 1,000 or 1,000. 1 in the fifth place means 1/10,000 or 10,000, etc. 0 is used to tell quantity and also as a placeholder to keep the other digits in their proper places. When 0 appears in a given place, it means none of that quantity. In the decimal system, each time we move a digit 1 place to the left, we, in effect, multiply it by 10. 1, 10, 100, 1,000, 10,000, 100,000, 1,000,000, etc. With the use of the digits 0 through 9, we can write a number of any size using the decimal system. In the binary system, we use only 2 digits, 0 and 1. Each time we move the digit 1, 1 place to the left, its value is multiplied by 2. For example, 1 in the second place to the left represents 2. 1 followed by 2 zeros represents 4. 1 followed by 3 zeros represents 8. 1 followed by 4 zeros represents 16, and so on, with the value doubled each time we move the 1 space to the left. The zeros are used both as a number and placeholder. The numbers in between can be expressed by simple addition of the place values of the 1s in the binary number. 3, for instance, is the binary number 11, meaning 2 plus 1. 5 is the binary number 101, meaning 4 plus 1. 6 is the binary number 110, meaning 4 plus 2. 7 is the binary number 111, or 4 plus 2 plus 1. Closed electric circuits can be used to represent 1s, and open circuits, 0s. In this way, we can count as high as 7 on 3 electric circuits. With 4 circuits, we can count up to 15. The closed circuits represent 1s in the binary number 1111 and represent the place value of each 1, or 8 plus 4 plus 2 plus 1, or a total of 15. By adding more circuits, we can record any number we wish using binary numbers consisting of 1s and 0s. Circuits that are closed represent ones. Open circuits, zeros. Binary arithmetic is practical for most computers because they contain many physical devices that can exist in one of two states. Initial data, such as the account number and amount on this bill, can be read automatically by an optical reader and fed into a computer for processing. Another system used to feed data to computers is automatic reading of magnetic ink characters, such as these at the bottom of a check. If data is fed into a computer from paper or plastic tape, groups of holes punched in the tape represent decimal and letter symbols. The computer converts these groups into true binary numbers for processing and then reconverts to the binary groupings that represent decimal and letter symbols for output. Letters, numbers, symbols, the data to be placed in the computer, can also be encoded on punched cards. Holes punched in the cards represent the letters, numbers, and symbols. This data can be recorded on magnetic tape by magnetic recording heads, whose poles may be north or south, corresponding to 1 and 0. The data on each punched card is recorded on a separate section of tape. The individual bits of information can be recorded in a very small space on the tape. The sections of information are called fields. Each field contains specific data of predetermined nature. Information to be fed into a computer is often encoded on cards, then transferred to magnetic tape for input to the computer. The cards can be recorded on tape at a rate of many hundred per minute. The tape can then be fed into the computer at a rate up to 120,000 characters per second. This data is stored in the computer's memory unit for use in solving problems. One type of memory used is the magnetic core memory, capable of storing millions of bits of information. Tiny magnetic cores threaded on wires store 1 bit on each core. A current of electricity passing through a core sets up a magnetic field that may be clockwise or counterclockwise, corresponding to 1 or 0. Thousands of cores are stacked in planes, any one of which can be located and addressed in millionths of a second. The size of the memory in this type of computer depends on the number of cores in the memory unit. In solving a problem, data in a magnetic core memory is stored, recalled, compared, calculated, checked, and restored at a rate of many thousands of calculations per second. For storage of data, some computers use magnetic drums that revolve at high speed. Minute spots magnetized on the drum's surface represent ones. Unmagnetized spots, zeros. Another computer may store information on rotating disks mounted like records in a record machine. A unit like this has a memory capacity of 5 million characters, any one of which may be located in a fraction of a second. Regardless of appearance, all electronic computers operate on the same basic principle, using simple language of coded signals, signified by circuits that are off or on. Let's see how we tell the machine what we want it to do. The plan outlining the solution of a problem is called a flowchart. The solution is often prepared by 2 or 3 people: an engineer, scientist, or economist who knows the particular problem intimately, an expert in computer operation, known as a programmer, who can lay out the solution in computer language. This flowchart outlines each step for solving an inventory control problem. A mathematician is usually required who can outline a method for solving a problem in terms of mathematical equations. resulting series of instructions for solving a problem with a computer is called a program. Special code is used for this program. It outlines in precise order the exact steps the computer must take in solving a problem. The last job of the programmer is coding, final translation of the program into instructions appropriate to the particular machine. Let's see how this problem involving stock inventory for a large department store is handled. Information about the thousands of small transactions that constitute the day's business is accumulated at the end of each work period. The program for processing this problem on the computer is encoded on punched tape. Information concerning the entire inventory for each department is stored on rolls of magnetic tape. These rolls of tape can contain the information from 2 million punched cards to be fed into the computer. Current transactions must be fed into the computer also. Given the necessary information, the computer console operator starts into action the thousands of electronic circuits. The control unit directs each step according to the program punched in the tape. The magnetic core memory unit stores information on the thousands of individual cores. 65,000 characters of information can be stored in this memory. Thousands of electric circuits like these in the arithmetic unit connect transistors that act as switches. The transistors are seen here as silver cylinders in the center. The arithmetic unit computes total sales for each department against inventory revision of the previous day. An inventory of 5,000 items can be processed by this computer in 5 minutes. The result is a daily record of departmental sales, a revised inventory, and purchase requisitions printed out at 600 lines per minute, telling buyers what items to reorder before stock is exhausted. The reams of tedious paperwork and accounting by manual methods necessary to accomplish this task would take hundreds of clerks several days. Such a task requires only a small percentage of the computer's work week. The remaining time, the computer is free to do payroll accounting, printing out as many as 90,000 checks in an afternoon, credit accounting, customer billing, and the hundreds of other arithmetic tasks that people would otherwise have to perform. The electronic computer has extended men's minds and multiplied their thoughts, releasing people from tedious, routine tasks to become creative. The thinking of students is tested with special examinations that are fed into a computer for automatic scoring. Computers are aiding medical research and developing new medicines. Control of one of the world's largest refineries is completely automatic, operated by an electronic computer a mile away. The jet age demands pilots trained to meet exacting requirements. This trainer, controlled by a computer, duplicates precise flight conditions without ever leaving the ground. Airlines use automatic air traffic control to handle thousands of flights daily. Airline flight plans are fed into a computer, filed, and compared with other flights in the area and with changing weather conditions. Flight instructions for each plane are automatically printed out, giving altitude and course data. Should there be a conflict with other flights, a warning is sounded, and alternate courses are given immediately. flight controller relays the new course to the plane.
Utah 18, have traffic northeast bound 12 o'clock, 2 miles.
Advanced rocket design and engineering would be impossible without the aid of many computers. New design features are simulated and studied on digital computers before building expensive models. Difficult problems await computers of the future. Areas of science present problems so complex that today's computers would require years to solve them. Computers of the future are being developed that demand of the men and women who work with them the utmost in precise and logical thinking. To meet this challenge, young people must begin early to develop a foundation of understanding basic mathematics and science principles. Computers do nothing voluntarily. Men must direct every process. The productive activity of people in the future will to a large extent rest in their knowledge of computers and how to use them. As computers relieve people of many tedious routine jobs, they free manpower to become brain power. The only giant brain that can meet this challenge is the brain of man.